of all, I want to thank the organizers for organizing this conference and inviting me to speak here. I want to talk about some joint work with Zhipeng Duan, Mike Hill, Guchuan Li, Yutao Liu, Guozhen Wang, and Zhou Xu. So in the title, you see higher real K theories. So to start my talk, I want to talk about K theories. So historically, K theories, together with their Bott periodicities and Adams operations, have been very useful at resolving various problems in algebraic and geometric topology. So here are some examples. The Hopf invariant 1 problem can be resolved by using Ku and its Adams operations. The vector fields on spheres problem is resolved by computing the Ko cohomology of stunted real projective spaces. And when Adams was studying the image of J, he used Ko together with spot periodicity and Adams operations to do it. So in all of these cases, K theory turns geometric problems into accessible algebraic computations involving periodic cohomology theories. So it turns out in chromatic homotopy theory, Ku and Ko, they belong to a more general class of cohomology theories called Lubin-Tate theories or Morava-E theories and higher real K theories. So here are my notations. My K is going to be a perfect field of characteristic P. Gamma is going to be a formal group law of height H over K. And I'm going to let EH to denote the Lubin-Tate theory associated with this pair K gamma. Okay. So here are some examples. If my K is Fp and gamma is the multiplicative formal group law as height 1, then the Lubin-Tate theory E1 I get is complex K theory, P completed. At higher heights, if my K is Fp to the H, and if my gamma is the height H Honda formal group law, then the EH I get is commonly called the height H Morava-E theory. So the Lubin-Tate theory EH, they're fundamental objects in chromatic homotopy theory. And the good thing about them is that they are also equipped with group actions. So here's a very nice theorem. Gorse, Hopkins, and Miller proved that EH is a commutative ring spectrum. It's E infinity. And there's a unique GH action on EH by E infinity ring maps. So here GH is the Morava stabilizer group. So the existence of this group action is really nice, has a very important consequence. Because now that we have a GH action on EH, we can take fixed points. So for a subgroup G in GH, we can take fixed points to get homotopy fixed points to get EH HG. So if I take G to be this full stabilizer group, GH, then Devanas and Hopkins showed that this homotopy fixed point is equivalent to the KH local sphere. What I can also do is I can take G to be a finite subgroup of GH. And these fixed points are, I'm going to denote them by EOHG. And they're commonly called the higher real K theories for the following reason. So at a prime 2, if my height is 1, and if I take my G to be C2, which corresponds to the formal inversion, then E1 is complex K theory, 2 completed. And if I take this C2 homotopy fixed point, I'm going to get KO, the real K theory, 2 completed. So for this reason, the EO theories, they're called the higher real K theories. So the EO theories, they're a very useful family of cohomology theories because they play an important role in detecting periodic phenomena in stable homotopy.
Can I ask a question?
Yeah, of course.
Is there something wrong with your uniqueness statement because there's also the trivial action?
Because there's also the trivial action. But it's the GH has to act, there's a condition on pi star. It has to act a certain way in pi star by the automorphism of the formal group. Okay. So the EH are very useful. So let me say some applications of the EO theories. So Hopkins and Miller, when these theories first came around, Hopkins and Miller, they computed the homotopy group of EOP minus 1 CP. So this is what happens if you take the height P minus 1 E theory as a CP action, so you take the CP fixed points. So they computed the homotopy group of that, and this computation was used by Nave to prove the non-existence of certain Smith total complexes. Also, these EO theories can be used to study the KH local sphere through the theory of finite resolutions. At height 1, this is done by Adams, Baird, and Ravenel. And at height 2, this is a program that was started by Gores, Hen, Mahol, and Resk, and has since worked on by many people. Also, the EO theories, they exhibit various forms of duality phenomena. And this has been worked on by many, many people. I tried to type in the names of all the people that worked on this, and I quickly realized they're not going to fit on my slide. So what I did is that I typed in the people who worked on this and who are here right now. So Toby Bartel, Paul Gores, John Greenlees, Mike Hill, John Rogness, Vesna Stoyanoska. So if you're here right now, you study this, and I didn't type in your name, I'm so sorry. Please let me know now. So they have various forms of duality phenomena. And also, if you care about the stable homotopy group of spheres, the EO theories, they detect important elements in pi star of S. So for example, the EO P-1 CP, this was used by Ravenel to resolve the odd primary covariant problem at P greater or equal to 5. And at height 2, the covariant problem was resolved by Hill, Hopkins, and Ravenel using EO4 C8. So there are very useful theories for detecting elements in the homotopy group of spheres. So here are some general questions we can ask for these higher real K theories. We could ask about their coefficients. Given these are cohomology theories, I can ask, well, what is the pi star of these cohomology theories? What are their coefficients? And if I have a space X, what is the EO cohomology of X for various X? Real projective space, complex projective space, quaternions. I could also ask about detection. What does their coefficients tell us about the stable homotopy group of spheres? I can also ask about duality. So what kind of dualities does the EO theories emit, and how does it look? There's also the periodicity question, which is the focus of this talk, is what are the periodicities of these higher real K theories? And there's also geometry, is that what can the EO theories tell us about manifolds and vector bundles? So what I want to say is that many people have studied these questions, and these questions, they're all related to each other. So in particular, the periodicity and detection of these EO theories, they play a key role in Hill-Hopkins-Ravenel solution to the covariant-invariant 1 problem, which is a problem about geometry. So I want to very briefly talk about the covariant-invariant problem. I know JD talked about it. I want to also briefly talk about it. So here's the question. So the covariant-invariant 1 problem asks, in which dimension is there a framed manifold with covariant-invariant 1? So in JD's talk, he mentioned how the covariant-invariant fits into this pretty short exact sequence involving the theta n's and the theta n BPs. So in 1969, Browder reduced this question to a question about the atom spectral sequence. So Browder showed that there exists a framed manifold of covariant-invariant 1 if and only if this element hj squared survives the atom spectral sequence to become an element called theta j in the homotopy groups, in the stable homotopy group of spheres. And since the theta j, this lives in dimension 2 to the j plus 1 minus 2, so a consequence of this is that the dimension of my manifold has to be 2 less than power of 2. So this is Browder's reduction. And 40 years after Hill, Hopkins, and Ravenel in 2009, they proved that for j at least 7, the covariant-invariant elements theta j do not exist. So as a result of their theorem, the only dimensions in which there exists a frame manifold of covariant rank 1 are in dimension 2, 6, 14, 30, 62, and possibly 126. So at the time when they proved their theorem, there's only one case left open, the one in dimension 126. And this was recently resolved by Lin, Wang, and Xu in 2024. So they showed that theta 6 exists. So as a result, there do exist a framed manifold of covariant 1 in dimension 126. So for my talk, I want to talk about the strategy that Hill, Hopkins, and Ravenel used to show that theta 7 onwards that they don't exist. Okay? So in order to prove their theorem, they constructed a spectrum, which they called omega, that models E04C8, okay, which is the C8 fixed points of E4. And then subsequently, they proved some theorems about this omega, about E04C8. They proved that omega is 256 periodic. It's the periodicity theorem. So pi star plus 256 of omega is equal to pi star of omega. Every time I shift by 256, I get the same answer. The second theorem is the detection theorem. They showed that the map, the Horowitz map from the sphere to omega, it detects the theta j elements. So what I mean by detect, it means that if the theta j elements are non-zero on the left, then when I map it over, it has to be non-zero on the right. And what we also know about omega is that we know pi minus 2 of it is equal to 0. Now this comes from something called the gap in the equivariant slice spectral sequence, which is a computation technique that they invented to analyze the homotopy group of omega. So once you have these three facts combine to show that the homotopy group of omega is 0 in these dimensions. For j, at least 7. Because if I plug in j to be equal to 7 here, I get 2 to the power of 7 plus 1, which is 2 to the 8. That's 256, which matches with the periodicity here. So if I know pi minus 2 is 0, and if I know it's 256 periodic, that means pi 256 minus 2 is also 0. And so on and so forth when I keep shifting. Okay? And therefore, since I know that pi star of omega is 0 in all of these dimensions, I know theta j do not exist. So that's how they prove their theorem. This is a motivational picture of this theorem that I really always like to put on my slide. It makes it really apparent what the theorems are doing. Okay? So this is like a baby version of omega. Omega is E04C8, and this is actually E02C4. So it's a smaller height, smaller group with a smaller periodicity, but it shows you what the theorems are doing. Okay? So the gap shows you that there's a gap. And this is apparent on the E2 page. You don't have to do any computation. You just get the E2 page, you get there's a gap. And the periodicity says that, so that square there, it's in stem 32 stem. The periodicity theorem means that this square, it doesn't support any differentials. It's a permanent cycle. It survives to the infinity page. So you see there are no lines coming out of that square. So that's what the periodicity theorem says. And it turns out, in this case, once I know there's a gap and there's a periodicity, I can automatically deduce that pi 30 is going to be 0 without doing all of these computations. So if I don't like to do computations, I just want to know what is pi 30, I can just be like, hey, there's a gap and there's a periodicity. So I want to move this 32 to the right. This is going to be pi 30, and that's 0. And if I move it 32 to the right again, I get pi 62. There are going to be more classes, but the gap in periodicity is going to tell me pi 62 is going to be 0 as well, and so on and so forth. Okay? So that illustrates the power of their theorems really well. I don't have to do computations to deduce the result on the level of homotopy groups. Okay, so here's the question I want to consider for this talk. It's, what are the periodicities of the EO theories? Now, I want to say is that it's a consequence of the nilpotence theorem by Devanas, Hopkins, and Smith that all of these EO theories, they are periodic of some finite periodicity. But what we don't know is that we don't know any concrete bounds for these periodicities, except at low heights, where we can do explicit computations on their homotopy groups. So we know the periodicities are finite, but we don't know what they are. So now the problem is that if I just know that these periodicities are finite, but I don't have any explicit bounds, well, this is not very useful for proving theorems or for doing computations. So here's an example. Let's say we're trying to prove the covariant problem by using E04C8. We know it detects the theta j's, and we know it's periodic. But we don't know, we only know it has finite periodicity, but we don't know the exact number. Then the only thing we can deduce is that theta j will eventually not exist. But we don't know exactly where it happens. It could be from theta 100 onwards, or it could be like over 9,000, like from theta 9,000 onwards. But we don't know exactly where it happens. And many more cases would have remained open if we didn't know the exact periodicity, instead of just theta 6. So it'd be very nice if we actually do have concrete numbers for the periodicities for the higher real K theories. So here's the theorem we proved. We call this the periodicity theorem. We proved that at a prime 2, for any height and any g a finite subgroup of GH, EOHG is PHG periodic, where this PHG is a very specific number. It depends on H and G. Okay, so this is how these numbers are defined. If you plug in an H, you plug in a G, this spits out the number. Roughly saying that, I'm going to show you examples in a sec, but roughly saying the number, as the height increases or the group increases, the number gets bigger. But you know exactly what these numbers are. So what this theorem does is that it gives the periodicities for all of these EO theories at all heights and all finite groups at the prime 2. Here are some examples, some low height examples. So at height 1, if H is equal to 1 and G is C2, I plug it in, I get this P is 8. And that's the real Bott periodicity, the 8 periodic. And at height 2, I can plug in different groups. I get EO2 C2 is 16 periodic, EO2 C4 is 32 periodic. That's the one we've just seen. EO2 Q8 is 64 periodic. EO2 G24 is 192 periodic. That's the K2 local TMF. And at height 4, I can plug in also different groups. I get 64, 128, 256, 384 periodic. And also, if I just let my group to be C2, I let the height to be any height, then I get EOHC2 is 2 to the H plus 2 periodic. So these are some examples. Okay? And these are actually the known computations by explicit computations. So what I want to say about these PHG periodicities is that it spits out the right numbers for all the known computations at low heights. So the PHG periodicities, they are sharp in all the previously known cases. And they're actually very useful for doing computations.
So that means they're not necessarily sharp in general?
They're not necessarily sharp in general. So right now, they're concrete bounds for the periodicities. And that's exactly what I want to say next. As in general, if we can completely compute the coefficients of the EOGs, the EO theories for arbitrary H and G, then we can certainly determine their exact periodicities. I just do the complete computation and be like, there it is. That's a permanent cycle. That's a periodicity. We're done. And this works when H is small, when my height is small, when I can do explicit computations. But the problem is that even though these EO theories, they're easier to compute than the stable homotopy group of spheres, they're all periodic, but they're still very difficult to compute for arbitrary height and group, especially when they get large. So even at low heights, at the prime 2, when my height is 2 and 4, the computations can get quite extensive to compute completely. But the good thing is that now that we have obtained the periodicities for these EO theories without doing complete computations, we can actually reverse this process to use these periodicities to help us compute the coefficients of the EO theories. So I want to reverse the flow of the information. Before we compute the coefficients first, then we deduce the periodicity. Now I have the periodicities without a complete computation. I want to use the periodicity to do the complete computation. Okay. So I want to give you a demonstration that uses the periodicity results to completely compute the equivariant slice spectral sequence of E02C4, the one we just seen. And this sort of justifies why I'm using slides. I'm the only person using slides for the talk. So I have a lot of pictures about spectral sequences. It's going to take a long time if I give a board talk. So this is the picture. This is the end result. I want to show you how you can deduce all the differentials here using the periodicity theorem. So I want to show you kind of a mini movie. So before that, there are some facts I want to sort of summarize. What are the facts? What are the structures about the spectral sequence that I'm using? So here are some facts about E02C4 and its slice spectral sequence. And there's the periodicity theorem that I just talked about. This is a 32 periodic theory. There's also a strong vanishing line. So what I also know is that there's a strong horizontal vanishing line of filtration 13. So what that means is that every class above the line of filtration 13 must die. That's what horizontal vanishing line means. What a strong means that the spectral sequence also collapses after the E13 page. So the longest differential in the spectral sequence is also of length 13 and most 13.
Which spectral sequence?
The slice spectral sequence, and also the homotopy fixed point and the tape. But all the spectral sequence computing these theories, they're all related. There's also the transchromatic isomorphism, which says that all the differentials, you see the spectral sequence had different regions, and the transchromatic isomorphism is telling you that all the differentials in a certain region can be determined by the differentials for the smaller height theories. So in this case, it's telling you all the differentials between the line of slope 1 and 3 are given by the differentials for E01C2, or I half the height, and I also divide the group by 2. You'll see that in a second. But this is telling you that there's an inductive approach. Once I compute the smaller height theories, I get the information at the higher heights for free. And the last fact I'm going to use is the existence of Tate periodicity classes. So there are certain classes that are going to be Tate periodicities. I won't have time to define exactly what they are, so I'll just say what they do. So the Tate periodicity classes, they help you to propagate differentials. So if I have a differential that I've proven, I can use these classes to propagate them over the spectral sequence. I can get more differentials. So they're used for propagation. So these are the 4 facts I'm going to use. Now before I start the movie, I want to just remark that these theorems work at all heights, not just for E02C4. So these are just the specific numbers you get when I specialize to E02C4. But these theorems, they work in general. All right, let's start. I say it's a mini movie, but it's a very, I click and click. That is, it's like that. It's not a fancy AI generated, none of that. Very basic mini movie. So this is the E4 page. So the reason I started with the E4 page is that the D3 differentials are all easy. They're all very direct. You can get them very easily. So the hard part is obtaining the higher differentials. You see there are some classes. There's the dot. So the black dot is a Z mod 2. Okay? You also see there's a circle. So the circle, that's a Z mod 4. You also see there's a red circle. So red circle is a Z mod 2. Why is it red? It was an actual circle on the E2 page. So it was a Z mod 4, but it supported the D3 differential. So then after it supported D3 differential, the generator of the Z mod 4 dies, and 2 times the generator survives. So I indicate that by a red circle. It's also a Z mod 2, but it's indicating that it was a Z mod 4. Now it's a Z mod 2. Okay? And there's just one other class. It's the square. That's a Z. Okay? So that's the 4 kind of classes you have here. Okay? Now, the first step is the transchromatic isomorphism. I take the region, that's the line of slope 1, and that's the line of slope 3. Okay? The transchromatic isomorphism tells me that all the differentials in these regions can be obtained from the computation for EO1C2, which is KO. So once I know that computation, I can just immediately import them over here. And I get all of these differentials for free. Okay, so what's left is I want to obtain all the differentials downstairs. Okay, how do I do that? I'm going to use the periodicity theorem. Okay. So what I'm going to do is I'm going to compare pi 0 with pi 32. On pi 0, you see is that, hey, there's just one square. And at pi 32, you see there's a square, and there are 4 other classes. Okay? So what the periodicity theorem tells you is that the end result must be the square, which is that square there, which means that all of these 4 classes, they must die somehow. Okay? So what I'm going to do is I'm going to look at the top class. The top class is very easy to analyze because the transchromatic isomorphism already took out all the dots here. So this class cannot support any differentials there. So the only way for it to die is for it to be killed by differentials. Okay. And what I also know is that I have a bound on the differentials by this strong vanishing line. So the longest length has to be 13. And this uniquely determines how this class must die. Okay. So I learned that this class must first be killed 2 times the generator here. It's a Z mod 4. So 2 times the generator must be killed by a D5 differential here. And the generator must be killed by D13 here. And this, the structures in the spectral sequence uniquely determines what happens in this class. Okay? There's a D5 and there's a D13. Okay? I'm just going to focus on the D5 because I want to get all the D5 differentials first. I have this D5, and now what I'm going to do is I have one D5. I'm going to propagate it. Okay? There's the Tate periodicity class in 8.8. I can propagate it. So I move it 8.8, I move it 8.8, I move it 8.8. So I got more D5s. And now what I'm going to do is I'm going to look at these 2 classes. These 2 classes are very early on in the spectral sequence, and I can easily prove that they are permanent cycles. So then what I'm going to do is I'm going to use the Leibniz rule. I use the Leibniz rule of this D5 with these 2 classes. I get more D5s. So I get 2 more D5s here. Okay. So now I have this group of D5s. And now what I'm going to do is I'm going to use the Tate periodicity again. Okay? So at the E5 page, there are 2 Tate periodicities. There's the 4,4 and the 16,0. So I can propagate by these classes. Okay? And I get a bunch of D5s. So starting from 1 D5, I just first try to move it down, and I get a little bit more D5, and I just propagate it all over. And this turns out to produce all the D5s in this positive cone here, this cone here. And then I use the Tate periodicity again. I can propagate all of these D5s through the Tate spectral sequence and then to the negative cone of the spectral sequence. I won't exactly say how that works, but I'll just say that once I have all the differentials in the positive part, I can just propagate them over to the negative part. And from here, I get all the D5 differentials. I started with periodicity. I apply all of these structures. I got all the D5s. And now I'm at the E6 page. Very good question. How do I know I have all of them? Actually, at this point, I don't know I have all of them. But that's the beauty of the computation, is that it's usually when you compute spectral sequences, like you are at the E2 page, you compute all the D2 differentials, and then it goes on the E3 page, you compute all the D3 differentials, and then after you compute all of them, you go on, so on and so forth. But for these computations, you actually don't know you have obtained. You don't know. You won't. It won't matter if you have obtained all the differentials, because as you'll see in a second, I will be proving different kind of length of differentials in one shot. So it's actually okay to. The beauty of these computations is we can prove different length of differentials altogether. So I actually don't know if I have proven all the D5. This could be the E6 page, or it could be there's still some D5 differential left. I don't know. But this is what happens if I take off all the D5 differentials I've proven. Okay, so now how do I get higher differentials? I'm going to use periodicity again. So I'm going to look at the 29, 30, 31, 32 step. And I'm going to compare that with this gap. So there's a gap here, if you remember. Pi minus 3, minus 2, minus 1 is 0. And pi 0, I have a z. Okay? So what this is telling me is that the periodicity theorem is telling me that only this square in this region gets to survive. And all of these classes, they must die. Okay? So if we can figure out how these classes die, I'll get a lot of information of the spectral sequence. So I'm going to look at this class first. This must die. There's nothing that can kill it. This part is empty. So it must support a differential. What's the only kind of differential it can support? It's the differential killing that class. That's a D13. So I got a D13 differential this way. Okay. Let's look at the next class. I'll look at this class. It must die. It can't support any differentials, so it must be killed. Okay. There are two possibilities. There's this class here, but if this differential happens, that's a D3 differential. And I actually have full control over the D3 differential. So I know for sure this D3 doesn't occur. So it has to be this class that kills it. So I get a differential this way. Green means D11. It's a D11 differential. Okay, so what's next? Next, I'm going to look at the 31 stem. There are 3 classes left over. They must all die. And there's nothing to their left, so they can't support differentials. So they must all be killed. And I also have a bound on the length of the longest differential. It has to be at most 13. So it turns out that's the only way. All of them must be killed by D7 differentials. Okay? And last but not least, in this region, I have that class upstairs that we just analyzed. We know there's a D13 differential killing it. Okay? So great. Now by using periodicity, I've obtained all of the differentials in this range. And now I can propagate by the Tate periodicity classes to get more differentials in the spectral sequence. Okay. And now what do? I'm not done yet. Let's keep going. Okay. There are more periodicities. We can milk more out of the periodicities. Okay. And next reason I'm going to compare is 25, 26, 27, 28. And then the part I'm going to compare is here. So here you see in each part there's only one class, right? And they all survive. So that means in this region, in each stem, there has to be exactly one class that's left. So the first stem we're going to look at is pi minus 7. That corresponds to pi 25. There are two classes here. The bottom one, by degree reasons, it must survive. Okay? And the top one, that means the top one must die. Okay? And the top one, the only way it could die is there's a differential killing like that. That's the D13. So then the next step. Okay, there are still 2 classes. The bottom one has to survive by degree reasons. The top one must die, and there's only one way for it to die. It's like that. And then this stem, there are 3 classes now. By degree reasons, the bottom one has to live, so the top 2 must die. They can't die by supporting differentials, and the only way is for them to be killed. And that's the only possibility. Okay. And last but not least, at 28, there's only one class left over here. That actually lives by degree reasons, and it corresponds to this class here. Yeah. So
the picture that you have there in the negative and up in the 20s, there's filtration. So there's periodicity, but there's filtration shifts.
There's periodicity, but there's also filtration shifts.
Like the filtrations of the 3 things that survive are like irregular, right?
Yeah, very good point. So Dan pointed out is that the green here and corresponding to the green here, the filtrations are obviously different. And that play a very significant role when I try to prove extension problems. That's a very interesting, that's a very good observation. That's important. Okay, so now I have more differentials. I propagate, I get more differentials. Okay. I'm almost done. To finish the computation, there's only one stem I have to compare. And that's the 4th stem with the 36th stem. So the 4th stem only have a red circle, that's a Z mod 2. And if I shift the 32 to the right, there's a circle, that's a Z mod 4. And there's a gray circle, that's a Z mod 2. But something killed part of it. So here, that's a Z mod 2, but that's a Z mod 4. So what you get is that the classes here, whatever happens, the end result has to be a Z mod 2. And it turns out the only possibility that could happen is for this class to support a D7 and for this class to be killed by D13. That's the only possibility it could happen. And after which, you're done with the computation of the positive cone. And now you use the Tate periodicity to propagate it to the negative cone. And you're done. Okay? Now, if the computation looks pretty easy, pretty automatic, it's supposed to be. Before, when you're doing these computations, you have to use restriction, transfer, and all of these formulas, and you have to do a lot of computations. But the point is that once you have all of these structural theorems of the slice spectral sequence, it's very hands-on. I can just tell the rules to maybe some middle school, high school student. It's like a game, right? It's like a board game, where I can, they can automatically use these rules to do the puzzle. In particular, I can feed it to a computer and for the program to try to compute it after I tell all these rules. Okay.
So can I ask sorry.
Yeah.
Information flow between the positive part and the negative part. You're saying, well, I know some things positively, and therefore I get the negative. And you were using a little bit, like in very, with low numbers with the gaps, to get back to the positive. But is it so? But are you ever really kind of using deeper information about the negative side to get information about the positive side?
I will be. So when I was when the height and the so the question is that here for the computations, I only use very shallow information of the negative side. I only use information here and compare with the information here. So the reason I did that is because here the information is very simple. And here the information is, there are a lot more classes here. So that's why I use the most simple information and compare with the hardest information to get the most information. But sure, you could have used information here and compare with the information here. You also could get more data this way. I chose the simplest way to do it.
There was an earlier question about how do you know that you have all D5s?
Yeah, so at this point...
didn't quite answer that, I think, because you made arguments that seem to depend on how many classes were left in various...
Yeah, so... Right. So so after I take off all of these differentials, how do I know I'm done with the computation? So once I get the horizontal vanishing line, once I see there's a horizontal vanishing line, then I know I have obtained all the differentials. Because the way that the differentials behave here, they're all very periodic. I couldn't have a differential somewhere here because they're very sensitive to the Tate periodicities. If I have a differential here, that must mean I get a string of differentials there. So the computations I do, once I've obtained enough differentials and I take them off, if I don't see a horizontal vanishing line, that means I'm not done yet. So I keep going. If I see a horizontal vanishing line, then I know my computation is finished.
John's question was slightly different. I think the answer might be something like, if there'd been an extra D5 that I'd missed, I wouldn't have been able to complete the computation.
Yes, yeah.
There would have been extra stuff.
There would have been an extra D5, then we would have proven. If I missed the D5 in the first step, then that D5 would pop up again when I do the computation. Okay. I've also marked all the two extensions by the dashed lines. I just want to say a few words about them. So the periodicity helps you to prove differentials, and it also helps you to resolve extension problems. So here, in order to resolve extension problems, I'm constantly comparing the information from the positive part to the negative part. I just circle some important ones. So for example, if I see this is minus 32. You see there are three classes here. There's an extension from here to there, and there's an extension from there to there. And they're pretty long extensions, and they're pretty hard to prove by hand. But if I have the periodicity theorem, I just need to compare it with pi 0. And there I just see a z. So I automatically know that there got to be extensions here. And similarly, if I look at here, there's a long extension here, right, on the 9 stem. So how do I know that one exists? I just compare it, move a 32 to the left. And here, pi minus 23, that's a z mod 4. So I know there has to be an extension here. So the periodicity really helps you to prove extension problems as well. Okay, that's the end of the movie, mini movie. I hope you liked it. Might be a little long, but so for the last 20 minutes I want to show you how we prove the periodicity theorem. So the proof uses equivariant homotopy theory. So recall that by definition, the EO theories, they're defined to be the homotopy fixed point of EH. So the idea is that EH, I should treat EH as a G spectrum and to study the ROG graded periodicities of EH. So the reason for doing that is I get more grading, and the more grading gives me information, much more information about the ROG graded periodicity of the EH. And the periodicity I want for the EOH is actually a linear combination of the ROG graded periodicities. So the linear combination of the ROG graded periodicities will give the integer graded periodicities for the EO theories. So here's a very low-height, very simple example. So if I want to prove the real Bott periodicity, I look at E1 as a C2 spectrum. I look at its ROC2 graded periodicities. It has two ROC2 graded periodicities. One is by the regular representation, it's 1 plus sigma. That's the C2 equivariant refinement of the complex Bott periodicity. Sigma is the sign representation. The other one is 4 minus 4 sigma. That's a ROG graded periodicity. That's a virtual dimension 0. That's something, so the 4 minus 4 sigma is something you don't see integrally. Because if I forget the C2 action, that's 0. Okay, now if I have two ROC2 graded periodicities, I take 4 times the first one, plus 1 copy of the second one, and I get an integer periodicity, 8. And that's the real Bott periodicity for KO. So this is the idea. So now that we know we want to analyze the ROG graded periodicities, I want to make a definition of the ROG graded periodicity lattice. So I'm going to define LHG to be the free abelian group of ROG that's generated by all the ROG graded periodicities, V. So this lattice encodes the complexity of the ROG graded homotopy groups of EH. In the following sense, it's because if I want to understand completely the ROG graded homotopy group of EH, I just need to understand the gradings in this quotient, ROG quotiented out by the periodicity lattice. So here's the example we just did. ROC2 is generated by 1 and the sign representation sigma. So L1C2 is generated by 1 plus sigma and 4 minus 4 sigma. And if I take the quotient, I get Z mod 8. And this is encoding the complexity of the ROC2 graded E1.
Are we still below the prime 2?
We're always at a prime, yeah. From the time when I stated my theorem, that was at the prime. But you could define this for any primes. But this example, all the example in the theorem, they're all at the prime 2. So this periodicity lattice is also useful for computing KH local Picard groups. Okay, now that we have this periodicity lattice, the goal is to analyze it and use it to obtain the integer periodicity for EOH. So I want to make some remarks. Is that in general, I have this periodicity lattice, LHG. It's actually very hard to completely compute it for arbitrary H and G, because that would involve very extensive computations of the ROG graded homotopy groups. But what we can do is we can analyze it inductively in 2 directions. So I have this diagram here. On the right, this LHG is what I want to analyze. And I have 2 directions. One I labeled transchromatic, the other one I labeled norm. So what does the transchromatic do? So it's a consequence of the transchromatic isomorphism. If my group is C2n, then if I have a periodicity in this smaller lattice that's a virtual dimension 0, then that has to be a periodicity for this bigger lattice. So what's this smaller lattice? This smaller lattice is LH over 2 G mod C2. This is when I have the height and half the group. So once I know some periodicities here, there will automatically be periodicities here by the transchromatic isomorphism. And the other direction is by the norm functor, which many people talked about. And in particular, Mike talked about it yesterday. So norm is that, what does the norm do? So if H is a subgroup of G, and if I have a periodicity V in this lattice, then I can norm it up. And norm acts by induction. So I get the induced representation of V has to be a periodicity in this bigger lattice. So these are two methods, two directions I can use to attack this bigger lattice using the information for the smaller ones. And surprisingly, these two methods, they give surprisingly good information about the bigger lattice. Okay. So I want to show you how this works for our theorem. But first of all, I want to specialize to some groups. So at the prime 2, if I want to study the periodicity lattice LHG for all finite G, this can be reduced to the case when G is a 2 subgroup of SH. And by the classification of the finite 2 subgroup of SH, I only get two kind of groups. The cyclic group C2n and Q8. So they're the only possible finite 2 subgroups of SH. So our focus will be to study the periodicity lattice for C2n and Q8. And here's what the method says for C2n. So for C2n, the transchromatic approach is going to establish an inductive approach to go from LH/2, when I have the height, and when I quotient the group by C2. And C2n quotient C2, that's a C2n minus 1. And the norm is going to give me a way to study this LHC2n from LHC2n minus 1. So I want to remark that if you look at the top and the bottom, both of these groups are C2n minus 1. But the way they're related to C2n is different. The top group sees C2n minus 1 as a quotient of C2n, whereas the bottom sees C2n minus 1 as a subgroup of C2n. So it turns out if I have information about the C2n minus 1 periodicities, I can actually get C2n periodicities in two ways. One is a quotient and one is a subgroup. So that's how I study C2n. If I want to study Q8, this is what I do. So Q8 has C4 as a subgroup. In fact, as 3 different C4 subgroups. There's the one generated by I, and the one generated by K, and the one for I, J, and K. So if I have a C4 periodicity, I can norm it up to Q8 in 3 different ways. So if I just have one periodicity here, I get 3 periodicities here by applying 3 different kind of norms. So I get 3 for the price of 1. Now this is an inductive approach, so I have to start somewhere. The place I'm going to start is the C2 periodicity lattice. And this has been completely computed. So it's a consequence of the real orientation theorem that Jeremy and I proved that LHC2 is generated by 1 plus sigma, so the regular representation, and 2H plus 1 minus 2H plus 1 sigma. So this has been completely computed. And that's the starting point. I was actually talking to Jeremy yesterday. I was like, hey, Jeremy, I also have some really good stories about us when we're undergrads and grad students. And Jeremy immediately freaked out. He was like, no. No more criminal associations. No more criminal associations. I was like, whoa, chill. They're fun stories. But then as I got to prepare the story, I realized they're not very math related. But I guess I'm being recorded and broadcasted, so I think I should continue with the math. So that's the starting point. It's the C2 periodicity lattice. Okay. And using this and this approach, this is the theorem about the ROG graded periodicities. Don't really read into it. All I want to say is that for this theorem, if my H is this number, then the EH has a C2n action. And we found a bunch of ROC2n graded periodicities. And if my H is this number, then the EH has a Q8 action. And here, we have also found a bunch of ROQ8 graded periodicities. And these ones, what do the symbol mean? So ROC2n is generated by 1, the trivial one, sigma, the sign representation, and a bunch of rotation representations. Okay. And ROQ8 is generated by 1. There are 3 sign representations associated to the 3 different C4 subgroups. So there's sigma I, sigma j, sigma k, and there's also a 4-dimensional quaternionic representation. That's H. Okay, so that's what all the symbols mean. And if you have all of these ROG graded periodicities, you can combine them, and you would get the integer graded periodicity as EO. So the theorem is a little hard to read. You don't have to read it. I want to show you a very low height example demonstrating how this works. So the example I want to show you is at the height 2. Let's say I want to find the periodicity of EO2C4. So what I should do is I should compute L2C4. And my approach is telling me I can study it in 2 different directions: the transchromatic direction and the norm direction. Let's do the top one first. I look at L1C2. 4 minus 4 sigma, that's a periodicity of virtual dimension 0. So this is telling me 4 minus 4 sigma is also a periodicity here. Okay. And now look at the bottom. So for the bottom, I have the regular one, the regular representation, 1 plus sigma. That's a periodicity here, and I'm going to norm it up. So 1 gets, when you induce it up, it becomes 1 plus sigma. And sigma, when you induce it up, it becomes lambda 1. Which is the C4 that's rotation by 90 degrees. It's a 2-dimensional representation. So I get this periodicity. There's also another one, the 8 minus 8 sigma here. I norm it up, and this is what I get. Okay. Now, this one might look a little messy, but what I can do is I can combine this 4 minus 4 sigma with this one. I can try to cancel out the sigma. I can combine it. And this is what I get, the 16 minus 8 lambda 1. And they're kind of color-coded to show you what's going on. So the 4 minus 4 sigma, that's in cyan. This one is in magenta. And I typed in GPT-4o, what happens if you mix cyan and magenta. It tells me you get blue. So this one is blue. Okay. So they're color-coded. So I get 3 different periodicities. And if I take a linear combination of them, I took 2 copies of the cyan, 8 copies of the magenta, 1 copy of the blue, I get 32. And that's how I get the integer graded periodicity for EO2C4. Okay, great. Now there's actually a bigger group as height 2. It's Q8. Okay. Now I have the C4 periodicity. How do I get a Q8 periodicity? I'm going to use the C4 periodicity I just obtained to get the Q8 periodicity. So I'm going to norm it up in 3 different ways. Okay. So this is how it works. If I take the regular one, then no matter which way I norm, I'm always going to get the regular one, which is 1 plus sigma I plus sigma j plus sigma k plus h. But if I take the other 2, the ones of virtual dimension 0, then when I norm it up, I'm going to get the 3 for 1. So if I take the 4 minus 4 sigma, if I norm it up using the C4 subgroup generated by I get, so the 4 becomes 4 plus 4 sigma I, and the sigma becomes sigma j plus sigma k. So this is what I get. But if I norm it out differently, I kind of permute the ij case. Okay? So I get 4 different Q8 periodicities using just 1 C4 periodicity. And similarly for the 16 minus a lambda 1, I get 3 different Q8 periodicities. Okay? So I have 7 periodicities in total. I can combine them to get an integer periodicity, 64. Okay? So from this, I deduce that EO2Q8 is 64 periodic. If that one looks a little unfamiliar to you, let me just multiply it by 3. So I get EO2G24 is 192 periodic. And that's the periodicity for the K2 local TMF. That's what EO2G24 is. Okay, so this is how, like a proof by example, how this method works. Okay, so let me go back to this ROG graded periodicity theorem again. What I can do is that now that I have all of these periodicities, I can define a new lattice. I'm going to define this LHG prime to be the lattice that's generated by these periodicities. It's a sublattice of the entire periodicity lattice I want to study, LHG. So how good is this lattice? It's actually pretty good. In fact, this LHG prime is a full rank sublattice of ROG. What does full rank mean? It means when I take the quotient, I get finite abelian groups. Okay? So it's a corollary of that ROG graded periodicity theorem that the complexity of the ROG graded homotopy groups of EH, they're finite with the following bounds. So at the cyclic groups, this is the quotient I get. And at Q8, this is the quotient I get. So not only I know that the integer graded ones, I know the periodicity for those, I actually have some control over the Q8 and the C2n periodicity lattice. They're all finite with this bound. And here you can pick out the integer graded periodicity. So that's the integer graded periodicity for C2n, and that's the one for Q8. And the rest is telling you the complexity of the ROG graded part. All right, so I got, thank you.
Thanks for that very nice talk. Does anybody have any questions or comments? Yeah.
When you were motivating your strategy at height 1, you derived the 8 periodicity of KO from the 1 plus sigma and the 4 minus 4 sigma periodicity. Is there a natural way of knowing the 4 minus 4 sigma periodicity without knowing the 8 periodicity, or was that just like a basic?
The 4 minus 4 sigma periodicity comes first. So the question is that I first had a 1 plus sigma, and then I had a 4 minus 4 sigma, and I combined them to get 8 periodicity. So you're asking which one came first? The 4
historically, the 8 periodicity.
Historically, 8 came first.
That's what I'm asking. How did you get the 4 minus 4 sigma?
It's via some light computations of the C2 fixed point of E1. Very light.
But also, Atiyah's original proof of the 8 periodicity goes via the 4 minus 4 sigma periodicity for the bigraded story. So Bot's proof is earlier, but the word Atiyah real refers to this.
Was there another question somewhere? John?
Could you say something more about the Tate periodicity elements?
Yeah, so the Tate periodicity elements, I think they're too far back. What they are is that they are elements that they're in the Tate spectral sequence. So there's a map from the slice to the Tate spectral sequence. In fact, to all different kinds of Tate spectral sequences, if I use the different families. And the Tate periodicity elements is that they're invertible elements on the E2 page. And they're all killed by the longest differential in the spectral sequence, whatever the length of that differential may be. And what you get from that is that once you have any, if you have any differentials, and if you multiply by those elements, you just get a bunch of differentials.
How did you find them?
How do I find them? That's a very good. So we found them by using the norm. So we looked at what happens for the smaller groups, and we try to norm it up, and then it's by the norm, by using the Hill-Hopkins-Ravenel norm.
Is there anything you can say about odd primes, especially the transchromatic phenomenon?
I was expecting that question. So at odd primes, there are several things that are available at even primes that are not yet available at odd primes. One key input for the transchromatic phenomena is you don't see that using the homotopy fixed points. This is something I guess Jeremy talked about. I said if you want to analyze something Borel, at the even primes, we're actually using something genuine to analyze it, at least like the Hill-Hopkins-Ravenel, these norms of the real Bordism theories. And at odd primes, as far as I know, we don't have genuine techniques yet that are effective at analyzing those. But I guess you can make some conjectures on what should happen at odd primes.
Are there any more questions or comments? No? Oh.
the middle part of your talk when you were analyzing the spectral sequence seems like every single thing you said could be pretty easily implementable by machine.
Yes. Lost the point. Yes.
Oh, sorry, Besma.
Sorry. So you said that these periodicities you got are not sharp, but yet you told us a method for how to compute the spectral sequence just knowing what we have.
Mm-hmm.
So are you hopeful that, maybe you could one use that method for computation to sort of decrease the periodicity or find if it's possible to decrease it?
Yeah, certainly. So now that we know a bound for the periodicities, that could feed into the computation, and then we could get more refined computations of the theories.
Right.
And once we did, then that would help us get more information about certain the orientation classes. And once we get more information of them, then we can try to reduce the bounds for the periodicity to make it sharp.
So since your answer is yes, do you have a sense for when would such a thing start being sort of different, if at all?
So our conjecture is that the periodicities are sharp. Unfortunately, because I feel like I like to compute stuff about these theories, and it would be very nice if the periodicity is actually smaller. That means I have to do less work. So, smaller periodicity, easier theories. But I mean, you do these computations, they're very extensive at first, but once you do enough of them, you start to see patterns. You get a feeling for the classes, and you kind of see how, not see, but you kind of feel, it's like, man, this gotta be all sharp. They kind of line up. I'll talk to you more afterwards. It's like, you can kind of see from the answer, they increase by the minimal one every time, so.
Okay, well, let's thank both the morning speakers.